A long-awaited promise of mobile robotics has been the autonomous exploration of environments inhospitable to humans. Mines present a wide variety of challenges, including challenging and complex terrain, inherent GPS and communication denial, and sensory degradation. Our platforms are Ghost Vision 60 quadrupeds, outfitted with Ouster 64-beam LiDARs, Radiant radios, PMD time-of-flight sensors, as well as thermal, stereo, and tracking cameras. Our exploration algorithm centers around tunnel detections. We take the panoramic depth image from the LiDAR, threshold it, and find the centroids of the resulting blobs to find tunnel candidates. These tunnels are tracked using a Kalman filter, and the current direction of the tracked tunnel is fed to the local planner. The local planner first fuses the LiDAR and time-of-flight point clouds. The fused point cloud is then converted into a 2.5D terrain map. From this terrain map, we can compute the gradient, integrate the gradient map using state estimation from the tracking camera, and finally generate a local cost map and configuration space that is used for planning. The terrain planner additionally feeds back information into the exploration model. If the tunnel that the robot is currently following becomes too challenging to traverse, it is marked as untraversable, and the next best tunnel is chosen. Missions are specified by sequences of turns. Here, the robot was given a right turn command. Once a right turn option becomes available, it immediately turns to face the new tunnel and starts heading in that direction. However, it rapidly decides that this tunnel is blocked and it cannot continue, at which point the tunnel is marked as untraversable and it returns back to following the main tunnel axis that it was before. Mapping is done using ICP and motion-corrected point clouds from the Ouster with a pose graph optimization backend. The mapper generates a sequence of keyframes spaced at several meter intervals. Here, note the pose graph adjusting as the distant April tag is added to the topological graph. Each keyframe has an associated depth panorama as well, and together these can be reconstructed into the global point cloud. The topological graph of keyframes, as well as the set of associated depth panoramas, is then loaded into the distributed database, and the base station is then capable of reconstructing the global point cloud. Artifacts are detected using a modified variant of EarthNet. Once an artifact is detected, it is localized using stereo depth. The local pose of the robot from the mapper is used to register the artifact to the last keyframe. A compressed image with bounding box is transmitted back to the base station to be viewed by the operator and transformed into the global DARPA frame. We additionally detect cell phones by listening for active Bluetooth devices.